Hello, this is Alex Howe with the Science Meets Fiction Exoplanets Review for February of 2022. If you're new to this series, this is where I look at all of the new scientific papers about exoplanets published in the last month on archive.org and summarize the dozen or so that I think are most interesting. I felt like there was a niche for a series like this on YouTube, so I decided to try it out, and so far it seems to be going well. Now, as always, this is only a sampling of the latest research in the field of exoplanets. There's a lot of great work being done that I didn't have time to talk about, and some of the most important work is inside baseball stuff that might not play as well here anyway. The hardest part of this process is choosing the best papers to include in the video, and if you want to learn more about the state of the field, I encourage you to take a look at the literature for yourself. Now, let's get started. I always like to start out with the new exoplanet discoveries, since that's the part that gets the most play in the popular press. There was only one this month that really stood out above the rest, but it was a big one. A candidate short-period sub-Earth orbiting Proxima Centauri. Proxima Centauri, as you probably know if you're watching this, is the nearest star to our Sun, sitting in a wide orbit around Alpha Centauri. So the fact that it has planets is pretty significant. And even more significant is that the first planet to be discovered, Proxima b, is surprisingly Earth-like. Now, keep in mind, Earth-like means a similar size and temperature to Earth, nothing more. But even so, that's a surprising coincidence. Proxima b is estimated to be in the ballpark of the same mass as Earth, and we estimate it to be a little bit cooler, but with a plausible greenhouse effect, it could be the same temperature as Earth. Proxima c is a larger planet in a much wider orbit, taking 5 years to orbit the star, which is a long time for a red dwarf. It's a sub-Neptune-sized planet that probably has a thick hydrogen atmosphere. The newly discovered planet, Proxima d, is interior to Proxima b, with an orbital period of only 5 days and in a Venus-like orbit. It's smaller than Earth and Venus, at only a quarter of the mass, but it could have very similar surface conditions to Venus. Now, that's the one major planet discovery we had in February, but there's always plenty of work being done to study planet populations. This is important to figure out how many planets there are in the galaxy and how many of them are potentially Earth-like. Although the first paper I noticed in this category is not to do with Earth-like planets. Precise radial velocities of giant stars 16, planet occurrence rates from the combined analysis of the Lick Express and PPPS giant star surveys. This paper is examining the occurrence rate of planets around giant stars, so more evolved stars near the ends of their lives. Now, this first figure looks at first glance kind of like the standard radius versus period diagram you see of exoplanets, but it's not. This is actually an HR diagram, showing host stars and also field stars. It doesn't look like the standard main sequence because it's specifically showing evolved stars. And you can see there are evolutionary tracks for stars of different masses drawn on the diagram. You have the subgiant branch of stars just beginning their trajectory toward a red giant in the lower cluster. The red giant branch moves up to the top right, and then the cluster moving across the middle is the horizontal branch. And this team looked at various surveys of exoplanets, looked at the number orbiting giant stars in their sample, and calculated the occurrence rate for giant planets, so planets larger than Jupiter, at a range of orbital periods. And the highest occurrence rate is for planets about the size of Jupiter with periods of about 1 year, where 5% of giant stars have planets in that bin. And they also show an occurrence rate by period alone, and cumulative distributions of occurrence versus period. And they break down the population in 2 ways: lower mass host stars versus higher mass host stars, and red giant branch stars versus horizontal branch stars. And the interesting thing is, there are more planets orbiting horizontal branch stars. Now, the horizontal branch is a later stage of stellar evolution, so if stars lose their planets during the red giant phase, which we think might happen because the stars lose mass, then those planets should stay lost in the horizontal branch stage. The authors say the difference between the two distributions is probably due to the nuances of stellar evolution, where more massive stars do not lose as much mass in the red giant phase. And long story short, the horizontal branch stars draw from a higher mass stellar distribution. You can read the paper to see the details. Another interesting survey comes out of South Korea, with mass production of 2021 KMT-net microlensing planets 1. I always think it's funny when I see astronomers talking about mass production of observations. Of course, we aren't really producing anything. Mass production just means we're doing a larger survey that will let us find a lot of a particular thing that was previously hard to find. And in this case, it's microlensing planets. Microlensing is sort of the dark horse method of finding exoplanets. It's the one that you tend not to think about as much unless you're actually working on microlensing. Microlensing happens when a star with a planet passes in front of a more distant star as seen from Earth. Because of general relativity, light from the more distant star bends around both the star and the planet, making it appear brighter. And the exact shape of that light curve tells us how massive the planet is and how far it's separated from its host star. And this particular survey, KMT-net, is the Korea Microlensing Telescope Network. And it is a project to take photographs of the galactic bulge, where stars are closer together so microlensing happens more often, with 2-meter class telescopes every 10 minutes. And that's a fair amount of effort to put into an exoplanet survey. They released their preliminary results in this paper with only 4 planets, which is already a decent haul for a microlensing paper, but they're expecting to announce a lot more planets in the future, so stay tuned on that one. Now, one indirect way to look for exoplanets is to look for signs of them in known planetary systems, such as in this paper, search for planets in hot Jupiter systems with multi-sector test photometry 2, constraints on planetary companions in 12 systems. And this is a paper looking for additional exoplanets in hot Jupiter systems. Because hot Jupiters are very massive planets orbiting very close to their stars, we expect them to have fewer additional planets in their systems. Because if they migrated to get to that location, they would have kicked all the other planets that were in the way out of the system. So here's the kind of results the author was looking at. This is a periodogram of the light curve, looking at what periods of additional planets are statistically most likely. And the author also looked at transit timing variations. And transit timing variations happen when there's gravitational perturbation of a planet, so that the transits don't always occur perfectly spaced. This is similar to how Neptune was discovered by its effect on the orbit of Uranus. And the author found no close planetary companions for these 12 hot Jupiters down to a sub-Neptune radius. And that's also consistent with other hot Jupiter surveys, so that supports this high eccentricity migration model for hot Jupiter formation. Now, when we're talking about TTVs, transit timing variations, we're usually talking about looking for additional planets in a system, but there's an additional application of them looking for long-term changes in orbital periods. And that is what Ivshina and Wynn did in test transit timing of hundreds of hot Jupiters. If you watched last month's video, you may remember WASP-12b, which shows transit timing variations that indicates its orbit is shrinking as it slowly spirals into its star. But this planet's orbit is actually shrinking at a quite high rate, so that it is very close to falling into its star in cosmic terms. And of course, this is a low probability result, so we would not expect to see it very often. And indeed, the authors looked at 382 hot Jupiters, and WASP-12b was the only one with a detectable change in its period. All hot Jupiters are expected to be spiraling into their stars, but only the most extreme cases would be fast enough to notice. So this is a null result, but in cases like this, null results can be good because they fit the theory perfectly. Now, some would say that's not as interesting as if they don't fit the theory, which is a fair point, but we have plenty of that going on in the field of exoplanets as it is. Speaking of tests, another paper looking at test data this month was Stellar Companions to Test Objects of Interest, a test of planet companion alignment. And this is looking at planets in binary star systems, and we know about half of the stars we can see in the night sky are binaries, and whether the planet's orbit is aligned with the binary star orbit. If the planet is well aligned, all the orbits are close to the same plane. But if it's misaligned, the planet might be orbiting at a completely different angle to the stars. And in this study, they just looked at the nearest star to each planet host, which often are quite far away, too far to measure their orbits precisely. measured the relative proper motion to estimate whether the stars were bound as a binary or not, and for the ones that were binaries, looked at the statistical distribution of orbital inclinations. Now, one thing that's very clear is that there are a lot fewer close-in binaries in the sample of planet host stars than in the field stars, the general population. And this is expected because a close-in binary will disrupt any planetary orbits that are close to it. And for this population, they calculated the expected distribution of inclinations for different scenarios. If the orbits of the planets are completely random, you get the gray distribution, which is pretty much just a flat line. If the orbits are circular but at a random orientation, you would get the blue distribution, which is concentrated around 90 degrees, which means on edge. And if the orbits don't have to be circular but are aligned with the binary star orbit, you would get the red distribution, concentrated around 0. And the results of their sample, for the Kepler planet sample, they get a little bit of preference toward the aligned distribution, suggesting there is some degree of alignment between the orbits. However, for close-in giants, they got the random circular orbit distribution, which is also expected, because hot Jupiters are notorious for not even being lined up with their host star's rotation, which is a much stronger tidal effect to align them. And this is just because they're very massive and have a lot of angular momentum. Now, interestingly, there was a second study this month that looked at this question from a somewhat different angle, a possible alignment between the orbits of planetary systems and their visual binary companions. And this paper looked at closer in binary stars that do have known inclinations, that are close enough that we can observe enough of their orbits to estimate the inclination of their orbits. And this plot is a cumulative distribution with how closely a planet is aligned with the binary star for binaries with known exoplanets versus a control sample of field stars. And the way this works is the control sample is binaries without transiting exoplanets. Most of these probably do have planets, because we know most stars have planets, but the inclinations of them will be random. If we compare that with a distribution of binaries that have known transiting planets, which are always going to be edge-on, we should see that the binary stars also have closer to edge-on orbits, and indeed that is what we see. So that's pretty solid evidence that whether due to tidal forces or probably more likely formation processes, planets do tend to align with the orbits of binary stars. Then, yet another paper looked at this question in terms of formation, misalignment of terrestrial circumbinary planets as an indicator of their formation mechanism. And this paper is specifically looking at circumbinary planets, which are planets that orbit both of the binary stars, so that the binary is very close together. And in that case, the tidal forces are much stronger during formation. So to do this, the authors simulated planet formation with a protoplanetary disk that was tilted a little bit from the binary star orbit, and another one that was highly tilted. And with the low inclination disk, as the planetesimals collide and interact with each other, they form a cloud of many tilted orbits, but they don't really get any more tilted than the original disk. They're just at random orientations. Then, as the planetesimals coalesce into planets, that cloud of particles will settle down into the plane of the binary star orbit, so that the planets will form pretty well aligned with that plane. However, for a highly tilted disk, the orbits become more chaotic and can have almost any orientation. And when they coalesce into planets, it turns out that you're most likely to get polar orbits at right angles to the binary star. And there's another important effect that the relative velocities between the particles are higher. That means when they collide, they won't stick together as well, and especially at short distances from the binary star, planet formation will be suppressed, because they just can't stick together. And this is a similar argument to the one I talked about last month about where planets can form versus where they would have to migrate from some other location. And if we see close-in circumbinary planets that are highly misaligned with the binary star, that does not fit with the formation model, so they would have had to migrate there. Now, for something a little more speculative, I saw this paper, Stability of Planetary Systems Within the S-Star Cluster, the Solar System Analogs. And this is talking about theoretical modeling of the S-star cluster, which is the cluster of stars orbiting very close to the supermassive black hole at the center of our galaxy. And there are a few dozen of them known. And the question is, orbiting this close to the black hole, at very high speeds, having encounters with each other as well, could they hold on to planets, or would the planets be gravitationally ejected? And the answer is about 50-50, with one big caveat. The authors simulated solar system planets orbiting around these stars in the S-cluster, and they found that about half of them were bound over the lifetime of the simulation. The catch is the simulation only ran for 1 million years, and for life to potentially arise on planets in the S-cluster, they would need to stay bound for hundreds of millions or billions of years. So a little more work is probably needed on that one to determine if those sorts of orbits really are stable. Moving on, I saw a couple of interesting papers about my particular subfield of exoplanet atmospheres. The first one, recycling of the first atmospheres of embedded planets, dependence on core mass and optical depth, is another one about planet formation. And this is talking about the first atmosphere of a planet, which is the hydrogen and helium acquired from the disk. For planets like Earth, that's completely lost. For gas giants, they mostly hold on to it. But while the planet is forming, and it's still moving through this gas disk, the disk is going to create drag on it, which the authors call a headwind. This is also known as ram pressure stripping in some contexts. And that headwind will blow away some of that initial hydrogen-helium atmosphere. Now, how much of it? Not a lot. For an Earth mass planet, it could be as much as an Earth radius worth of gas, but this is very early in the process when the atmosphere is several Earth radii thick, and quite possibly none of that gas will be retained. Still, in the most extreme case, they calculate that as much as 1/4 of the initial hydrogen atmosphere could be stripped away by the headwind from the disk. So that could be a significant statistical effect on exoplanet populations that we might want to account for in future atmosphere models. And the final paper for this month has to do with everyone's favorite exoplanet topic, looking for life. Understanding planetary context to enable life detection on exoplanets and test the Copernican principle. The Copernican principle, of course, goes back to Copernicus, and it simply says that humans are not privileged observers of the universe. Or in more concrete terms, Earth and our solar system are not exceptional places in the universe. This means we should expect the rest of the universe to appear similar, although the field of exoplanets has found a lot of strange things that are different, and it suggests that life should be common in the universe. But the trouble with this idea is that we need to be very careful in testing it, because while we haven't found signs of life, we have thought up a lot of ways that we could potentially find false positives for life. And that is what these authors are saying. If we're looking for biosignatures like oxygen or methane, it's very important to understand a planet's context to determine whether it's likely for life as we know it to be there in the first place, and to consider all the possible sources of false positives like volcanism or impacts, or just something like Saturn's moon Titan that has a lot of methane naturally. So this paper goes into a lot of detail looking at possible false positives for biosignatures like methane, and how to hopefully rule them out. So that's the state of the field in February of 2022. Be sure to like and subscribe for more exoplanet content. And I've got a new video about my own research coming out tomorrow that I think you're really going to like, so be sure to check that out.